Okay. Thank you, Mike. Hello, everyone. I'm Ms. Shiyong from Baidu. Today, I'm very glad to be here to share with you some ideas about Baidu's AI hardware infrastructure and hope to have a good discussion with you. The main contents I share today include the following aspects. First of all, let's have an overview of Baidu's AI hardware infrastructure. In order to solve the problems of all aspects of the AI system, we have built a full-stack system architecture from chips to frameworks. Second, the most important part of the infrastructure is AI computing system. Here, I will briefly introduce our latest X-MAN 4.0. The third is about storage and communication. In order to make the AI system powerful, we designed special storage and communication acceleration components. Finally, with the help of Kubernetes, we have built an AI distributed training platform, Kongming, which can make full use of our AI computing resource. Okay, as we know, an AI task contains the following stages: data loading, pre-processing, forward computing, backward computing, which requires all components of the AI system to work together. The bottleneck of any component will affect the performance of the whole system. Therefore, the design of AI system needs to consider the following challenges: computing, storage I/O, communication, and scalability. In order to confront these challenges, Baidu built a full stack of AI infrastructure, from AI chip to framework. First of all, with the help of software and hardware co-design, we have designed an AI chip, Kongming, which has a powerful performance. In the hardware system layer, we designed a powerful AI computing system, a broad storage system, and a high-speed communication solution to meet the system challenges mentioned above. We also built some optimization tools or acceleration components in the optimizer or optimization layer. The third, AI system is very expensive. With the help of the cloud-native Kubernetes, we built an AI training platform, Kongming, with flexible and intelligent scheduling. We can make full use of the underlying computing resource. Next, I will give a further introduction to the hardware system, software optimization, and cluster scheduling. First of all, I will introduce Baidu's AI computing system X-MAN. X-MAN is an advanced AI computing system. In the year of 1.0, we began to explore a more advanced hardware solution. Through hardware pooling, we can expand 64 GPUs in one node. In the 2.0 year, we began to explore the solution of liquid cooling in high-performance servers. And by enabling NVLink, we can achieve more efficient GPU interconnection. In the era of 3.0, modular design brings more flexibility. And we also started to use 48-volt power supply to get more computing performance. In the latest X-MAN 4.0, we mainly focus on the design of interaction and I/O, which can give more scalability, so it can be better compatible with HPC. The latest X-MAN 4.0 has the following features: modular design, flexible topology, up to 24 cards, and in order to compatible with HPC, our I/O design is more flexible. We not only have the high-speed interconnection of NVLink within the nodes, but we can also construct very powerful GPU clusters through network. So it's a very flexible architecture. In addition to the design of X-MAN 4.0 based on NVIDIA, we are also actively building OAI ecology with OEM manufacturers. Inspire has designed the OAI system, and we are actively introducing OEM partners, such as Havana, AMD, and so on. In the AI system, we also need to solve the problems of data storage. In order to train a high precision model, we often need to process large-scale data. But each data is a small file, such as picture and text. In addition, we also expect that the system have low latency for loading data. In order to make full use of GPU, summarize, the AI storage system hopes to have the following characteristics: large capacity, small file supporting, or low latency. In order to meet these requirements, we adopt the pooling storage solution in hardware, which realizes the high bandwidth and low latency between computing nodes and storage nodes through RDMA. And this decoupling design will also make the expansion of computing and storage nodes more flexible. In addition to the pooling design hardware, we also have designed a distributed file system, BPFS. The file system has many optimizations for small files, such as SPDK, RDMA, and long locking design. The whole system has achieved very good performance. And the whole system, and the whole file system also provides a complete POSIX interface, which is convenient for users to access and use. We have selected some typical models and services to test the performance of BPFS. It almost achieves the performance of the local disk, and the training performance is significantly improved compared with other common distributed file systems. For communication, we have also built an accelerated computing component, Hello. In an AI application, there are many deep learning frameworks, such as TensorFlow, PyTorch, PyTorch, and some other private frameworks. Using these frameworks for distributed training, we always encounter some problems. Either the use is very complex, or the performance is very poor. From another perspective, the underlying communication mechanisms are also diverse, including traditional MPI, communication mechanism provided by chip manufacturer, such as Nickel. So a good communication framework should be compatible with these hardware and software constraints. In addition, the communication in AI training often needs to transmit gradient information, which has the characteristics of small data, frequent interaction. Therefore, the ability of gradient compression is a common optimization. This compression may give the better performance. We also selected some common AI models and tested them. Compared with the open source Harvard, we can achieve 10% to 30% performance improvement. Based on Hello, we also consider more optimization to obtain better communication efficiency. Finally, in order to find the bottleneck in the system, we also developed a systematic resource monitor, BPFS. We can get system bandwidth, component utilization, and time slice in each stage. which can get the optimization of software and hardware design. The above is the optimization design of some hardware and software. In order to improve the overall software resource utilization, we have built a large-scale distributed training platform based on cloud-native kubernetes. In the training platform, we use hierarchical design to optimize the efficiency of task and the resource. First of all, in the bottom layer, hardware access layer, we use Kubernetes device plugin mechanism and our own GPU solution to achieve efficiency GPU sharing technology, which can make better usage of GPUs. In the resource scheduling layer, we achieve efficiency and intelligent resource scheduling through twin job operator, autoscaler, rescheduler, and other technologies to ensure the efficiency use of the cluster resource. Finally, in the task scheduling layer, we achieve a fair task scheduling mechanism through the queue management, task management, and other modules to ensure the efficiency operation of training tasks. In this way, through the cluster management technology of the whole stack, the whole intelligent and efficiency AI training platform is constructed. First of all, training job operator. The resource required by AI training task have a feature. It requires all GPU resource to be ready to run. Kubernetes doesn't support this resource scheduling. Therefore, we implement a training job operator to realize GAN scheduling. In training job, we defined all the resources required by a training task, including GPU, CPU, and memory. And the parameter server is automatically allocated in the underlying implementation. If all resources are sufficient, all resources will be allocated. Otherwise, no resource will be allocated. In the Kongming platform, the second major ability is intelligent scheduling. Here I may introduce three features. The first is preemptive scheduling. Baidu training tasks are diverse. Running time is also very different. So the priority of this task is not the same. Some of them need to run as quickly as possible, while others can run for a long time. Therefore, we design a preemptive scheduling strategy. The high priority task marked in red above needs to 3 GPUs, and there is no ready resource at present. Then the scheduler will preemptive for the low and the medium priority task. Later, the scheduler will resume the preemptive job by the checkpoint of the framework. Okay, the second aspect of the intelligent scaling is shared scaling. GPU itself doesn't support multi-task allocation. That's to say, GPU is either assigned to task A or task B. However, in practical application, some tasks cannot fully use the allocated GPU resource, especially some small models, which will lead to inefficient utilization of GPU. So we design a CGPU solution, which allows multiple tasks to share a GPU. These tasks will separated from each other. At the same time, we also use NVIDIA's tools, MPS, to fuse the multitask context of the shared GPU, which can further improve the application efficiency of resources. The third aspect of the intelligent scheduling is topology awareness. As we know, AI server involves a lot of interconnections, including the interaction between CPUs and the PCIe and the interaction between I/O and GPU. The topology awareness also brings efficiency resource utilization. Finally, the function of flexible scheduling is also provided in Kongming cluster. In the actual running process of the task, we may encounter that the resource may be insufficient, and we need to adjust the resource dynamically. In the case of not supporting elastical scheduling, the common operation is to delete the task, reallocate the resource, and restart the task, which will lead to a waste of resource and time. So we use checkpoint mechanism of the framework to realize the flexible scheduling. When a resource needs to be adjusted dynamically, we suspend the current task. After adjusting the resource, we use the checkpoint mechanism automatically saved by the framework. We redistribute the data distribution and reconstruct the whole training task, which can greatly improve the training efficiency. In addition, depending on the same mechanism, we can also implement the rescheduler mechanism to reallocate the resource of running task and improve the utilization efficiency of the overall resource of the cluster. Summary, I introduced the main contents of Baidu's AI infrastructure, from the bottom hardware system to the intermediate acceleration components to the upper scheduling platform. Combining with the bottom chip, AI chip and the upper framework, we realize the full-stack AI architecture. In the hardware layer, we are also actively promoting OAI ecology, hoping to bring you more software and hardware solutions. Okay, that's all. Thank you.
Thank you so much, Shiyong. If anyone has the call, if anyone on the call has any questions, please feel free to unmute and ask. And if anyone watching, I think there's about 40 folks watching. If you have any questions, please feel free to drop those in the chat. But thank you so much for your presentation. Really interesting to hear what Baidu is doing.
Okay, thank you.